So what is the final goal of the agent in this environment? So the agent starts to play. It's going to do an action. It's a reward, get some observation. Based on them, it decides for the next action. And it keeps on going like that. Now, the point is that it wants to probably maximize what it gets from time t on, right? Now, this is what we call it the future return. So it means that when we are playing, when the agent is playing, at every single time, it just cares about making whatever comes after that maximum, right? Now, you might tell me why we define this future return. And, well, this is a bit of philosophical question, so I cannot answer you for sure. But there are a bunch of, motivational answers. So, first of all, I mean, reward is the only thing that it thinks of, right? So it's a machine, and we think that reward is a good thing, right? So nothing, not money is not everything, of course, yeah, but reward includes everything, right? Maybe money and a bit of morality and a bit of, flexibility and a bit of other things. We think that it is defined well enough that motivates the agent to just do maximize it for any cost, right? And this is the first thing. And the other thing is that why it's looking for the future only. I mean, that, I guess it makes sense for you because whatever has been before is over, right? So you cannot do anything for the rewards you collected already. You want to just improve the rewards toward the future. And one other thing is that sometimes in many board games and other things that you do, you gradually start to get this idea that if you want to get a very good reward towards the end, maybe you should compensate a few steps next, right? So maybe you're not always looking only for the next reward, right? When you start playing chess, you do not do these crazy moves like you take the bishop and just hit the hit the queen right away, right? Because you know that there are going to be consequences. Yeah. You give it infinity, right? This is the point that I told you, but that we are going to shortly define the state. And once we define state, this confusion is going to... No. So that's it, but as I said, this is a bit of philosophy. So you have all the right not to take it, say this is not a very good behavior by the agent. Then you are just, from then on, you should accept that we're investigating a kind of bad creature called agent, and a devil creature called agent who only cares about the future return. But given that, we are going to define future return. So future return is what the agent cares about. This is going to be this one. So G is the return that I'm going to get from time t on, right? So when I move my action in time t, when I do AT, I start to collect rewards, right? And from then on, whatever the reward is, I'm going to keep it inside this summation, and this is going to give me the future return. Now, here, first of all, let's take a look at the index here. So if I do action at time t, the next reward that I'm going to get is rt plus 1, right? And then I go and do the action at t plus 1. I'm going to get rt plus 2, and so on. So I'm going to have rt plus I plus 1 infinity. So it's going to be r plus 1, t plus 2, rt plus 3, and so on, right? So this is the time sequence, right? Now, I have another factor here. I show it by gamma. And this factor gamma is something between 0 and 1, which is counted. Okay? Now, if you put it 1, it's going to simply be that you're just collecting everything in the future, right? But you can give less value to the future as well, right? This is why the main reason we need it is because in some games, or some environments with very dense reward, like every time you get reward, then in order to make this sum to converge, you need gamma to be smaller than 1. Like you put it exactly 1, and then you sum up 1, 1, 1, 1, 1. It's not going to converge, right? You need to make the series converge. This is the main mathematical reason to put it, but it also makes sense in many applications. Okay, now let's just break down this discount factor first a bit, just get a bit of feeling about the future return, and then we're going to go for the next step. So if I open up the future return is going to look like this. So look at this term. The first term, this summation, the first term is going to be when I set I equal by 0, right? When I put I equal by 0, it doesn't matter what is my discount factor, right? This is always going to be 1, right? Anything to 0 is 1. It's going to be 1, RT plus 1. Next one is RT plus 2 times gamma, RT plus 3 times gamma squared, and so on. So it's going to be like this, right? Next return, the second next return times the discount factor. The third next return times the discount factor squared, and so on, right? Now, the thing is that this RT plus 1, we usually call it immediate reward. This is the thing that we immediately see after we do the action, right? And in this formulation that you see, if I set gamma to be smaller than 1, then I'm actually giving the immediate reward more weight as compared to the you prefer to have your profit or money right now rather than a few years later, right? There is inflation, many other things that makes the same amount of money in future less valuable for you, right? So this is the philosophy of this discount factor there. I mean, it makes total sense, but some people might say that, I mean, there are some applications where this is not really working, right? In that case, you can simply set gamma to be 1, okay? So you usually consider a discount factor. As I said, this is we prefer to have sooner than later, right? Now, there are two different kind of look here, so two extreme choices for discount factor. You can set discount factor to be 0. If you set it 0, then any term from the second towards the end, it's going to be 0. This means that you're going to just look for your immediate reward. This is what we call it short-sighted agent. This is like you just look for the next time, right? You don't think for the future, right? And then you could be a bit thoughtful and you give it more time, right? So you can give a bit from the future. Very extreme case, you might be super conservative and you gamma equal by 1, meaning that you just care about the very future as much as you care about your immediate reward. Okay? Everybody's clear? So this is the return that this is the thing that we expect, or we care about, and we want to somehow play in a way that this future is going to be maximized, right? Now, we want to maximize the future. Every single time when we want to decide for our action, the thing that we are going to do, we have a history behind us. We'll look at everything in the history, and we decide to take the action from the action set, which is going to give us, or we expect that, it's going to give us the highest future return, right? Okay. Now, the key point here is that if you want to do this, if you want to do it in this framework that we have here, if you don't add any sort of formulation of the observation that you have, you're going to get into a trouble. And the trouble is that say I can describe this environment with some weird logics, right? So say this is a actually a robot arm or a robot, a real robot, and then you're just designing the action of the joints and the movement. And all of them, I mean, depending on the action that you do, you can explain what's going to happen if you do know all the physics of the environment, right? It's going to be a super complicated thing, not practical, but theoretically you can do it. But even if that is the case, still you're going to have a big problem. And the problem is that if you want to really do this, at every single time, you need to have the whole history in your buffer, right? So you need to know what does the robot has, what kind of move the robot has done on the very first time step towards the current time step. And if you want to leave the robot in the nature, this is pretty much impossible, right? So theoretically, you cannot collect all of those returns forever. You cannot keep all of the history forever. And this is also something that is not happening in practice. And because of that, this is why we are going to just model everything with the random random formulation. Analysis is hard, and also we do not have, theoretically, we do not have infinite memory to keep all the history, everything. So we are going to look at this environment to be a kind of random object. So I do understand that some of you might say many environments that we are working with, it's not theoretically a random, because if we have a huge computational power, we can explain that environment perfectly. That's correct. In the robot example, that's the case. But at the end of the day, this is computationally infeasible for us, right? This is why thinking about the environment to be a random object is actually a very concrete mathematical form. And the point is that even if the environment is really deterministic, or random formulation is going to reduce into that deterministic form by setting everything properly, okay? So it's a kind of more general formulation. Now, what we are going to say, we're going to say that depending on the action that the agent does, then there is going to be a reward and an observation. And these rewards and observation are coming from some distribution, right? So you can think of the environment to be a kind of random generator. It's going to look at your action, and then it's going to generate some random reward and observation. Clear? Okay. So agent is the agent again looks at that things coming from the environment and tries to do it. The agent itself can again do the action randomly, right? It's going to see whatever it has through the history, and based on that, is going to just act maybe randomly. For example, in the multi-arm case, multi-arm bandit case, we had the random strategy as well, right? So I told you work first day A, second day B, and then from then on, you're going to work for A if A is paying more, B if B is paying more, right? But can you tell me where are you playing on day 3 from very beginning? No, it's still random, right? It depends on the payments coming from the company itself, right? They are random. Your action is random as well, right? So now the thing that I want you to start gradually feel is that this agent and environment, the best way that you can explain their interaction means is to just describe everything by random processes. So you have your agent looking at a few observations. These are realizations of random things. Based on that, it's going to just decipher something. This could be potentially a random. So it sees something, and given that, it's going to generate some action, which is potentially a random. And then based on that action, again, the environment looks at the action, and given that action, is going to generate a reward and observation. Okay? So now, yeah, so this is eventually what I said, so I forgot the animation to be completed. So now, if we want to formulate the way that I told you, yes? Yes. Yes, yes. Yes. Definitely, yeah. Yes. You can add, like, for example, the exploration. Get into no question? Okay. So if you got no question, and let's get to the notion of state. Okay. Now we are gradually getting there. So this is the final formulation. Now the environment, as we said, it's going to be a kind of random object, right? This guy looks at your action and gives you some reward and some sort of observation. Now, if we really want to think about it, that we have this whole history forever, and then at every single time, the thing coming out of the environment is somehow depending on this whole history, then the memory of this environment should be infinity, right? Because, I mean, eventually at some point in time, any environment with limited memory, which is the case in the nature, right? Nothing in the nature has infinite memory. So anything on this nature at some point of time is going to get full in the memory, and nothing is going to, yeah, I mean, you cannot keep the whole history in there, right? So because of that, so as t goes to infinity, the memory that is collecting all of this history is going to get infinite. And this means that the environment is going to get full in the memory. One thing that I want to just give you give you a bit of attention here, a remark here. I'm not talking about the memory on your computer simply, because that is, of course, one kind of memory. But when I talk about the memory, I really mean like the nature, right? So, for example, the weather, right? The weather has a limited memory again, right? You cannot say that today weather is really depending significantly on the weather 2,000 years ago at some particular day, right? That's not happening, right? Do you get my idea of memory here? So I'm just talking a bit abstract here. So by memory, I mean that anything in nature, whatever you see of it, is going to depend on a few things before, right? That few could be very large for some natural things, right? But at the end of the day, it's limited. It's not really mathematically going to infinity, right? It could be very large, but it's not infinity, right? So because of that, we can't find something that we call it state, okay? I'm sorry if it was a bit confusing, but once the state is there, then everything gonna get clear, okay? But I found it the best way to justify that we need a state here. So, this is the moral story that I want to say. Like, if I have this very long history, at some point of time, is going in this nature is going to collect all of those infinite information, because that is eventually not the case, right? We don't have infinite information in this nature. So this is why we need to just define something which is carrying information, a finite amount of information, infinite in time. And do you have any idea what kind of thing that could be? If you have one environment, say you have the weather, right? And then you want to talk about the weather today or tomorrow, okay? Then you typically do know that it's getting, like, you are not going to say, like, this is the last day of this universe, right? This is not going to happen. So the days go forever, right? But every day that you want to decide what you're going to say, you are going to look at a finite number of days before, right? And you're going to say, these are the days which are going to impact. Anything before it, it's eventually having so much tiny impact, or maybe nothing, that I can simply ignore it, right? So now when you go the next day, what's going to happen to that memory? The last day that was in the memory going out, the new day replaces, right? If you're looking at the last 10 days, today you're looking at the last 10 days. Tomorrow you're looking at the last 9 days plus tomorrow, right? Yeah? You see it? So you're going to carry this finite memory infinitely over time. And this is the notion of state, right? I don't know if you had the course deep learning, but indeed get into analysis of sequences, we again talk about the same thing, right? State-dependent system. So any system that has a finite amount of memory which can carry over time for infinite, then you can represent it as a state-dependent system, right? So there is one state, that state could be giant, but it's again finite, right? And then everything in the future depends on that, the current state, right? Everybody's cool? Questions? No question? Yes, because it's not like they are not relevant at all, but they have some impact on your current state, and all of the information that you need about them is available in your current state, right? So you can just look at your current state, right? So it's true that the was, I don't know, last summer, right? Not this summer, last summer, right? As well. But the key point is that the temperature in the last couple of days were also impacted. Need to predict the temperature tomorrow is within them, right? So yeah, that day is implicitly impacting your decision. But you really don't need to just look at all of them, like from beginning of history, from Big Bang to today, to the temperature, right? You don't do it, right? You get my idea? Yeah. So yesterday temperature depended on the previous day, right? And the previous day and so on. But if you want to just talk about tomorrow, you just look at yesterday, right? And then you would say, okay, if yesterday was warm, this is because the day before was warm, right? And the day before was warmer than usual and so on, right? But you don't expect that tomorrow is now going to be very cold, right? Because yesterday was warm. I don't expect the temperature change more than something, and that it's not going to happen, right? So did you get the idea of the state I mean? Yeah. So this is the idea of state. Memory that the nature has is limited, right? And because of that, you only need the current state. Yeah. if you got no question, then I hope all of this philosophical discussion we had convinced you that we can model the environment as a kind of state-dependent system. Okay? And this system has a bit of randomness inside it. So it's random because we don't know all the physics, and it's a state-dependent system because it does not have infinite memory, right? And then you can think of it in form of one system with one state, which is just changing the state through time. Now, let me first define the state. So the state-dependent environment is one environment which at every single time that you are going to do your action, it has a state. Now, again, like the action, reward, other things, I'm assuming that the state is coming from a finite discrete set. Is it necessarily the case? No. When we get into deep RL, we're going to get rid of this assumption, right? But now we're going to consider it because it makes the formulation rigorous. Now, I have this state at every single time, which could be one of the possible n states, right? And then each time that the other side does an action, my state is going to change from one state to another, right? Now, when next time I look at the action coming from the agent, I don't need to go back and check the previous states. Whatever the state is, that action is going to make that state to change again to another value. Everybody's clear? Okay, cool. So this is the set of possible states, and as I said, it's not necessarily discrete, and it's not necessarily finite, but we keep on assuming that because that's going to make the life much easier for us. Okay? Now, given this state-dependent formulation of the environment, now we can concretely represent everything. So I have the agent, I have the environment. And now this environment is going to be represented only by the state. Okay? That's only the state which is going to represent this environment. Now, this guy is going to look at this state. Now, you could see the complete state. This is the ideal case. This is the thing that we are going to consider when we are formulating everything. But in practice, you might see a part of state. And why do I say a part of a state? Because when we talk about the example of weather, can you conclude kind of state that you consider, like the temperature in the last 10 days? Can you conclude that this is enough state? No. There is one state. Maybe that is the temperature of the last 5,000 days. You don't know, right? Maybe in addition to that is the amount of moisture you have in the weather and a lot of other things, right? You don't know what is this state, but you can imagine that state exists, right? And looking at that state, the next state after doing any action is going to just change that state, okay? But you might not see all of it. The best example is the example of chess, right? Like, there is one state that you're seeing, right? And this is exactly the board of the chess that you see, right? Now, it might be that you include the mindset of the other side into this state, right? Like the guy who is playing with you has a specific mindset in one specific is going to do its own specific move, right? But you don't see it because you are not inside the mind of that person, right? You just see a part of this state, which is invisible to you, right? So you have incomplete version of it, but I told you in most examples, in formulation that we consider, we always think that we have access to the complete state. When we don't have access to, we could say that, okay, the amount of things that we don't see is going to somehow be added into the randomness of the environment. Okay? Now, based on this observation of the state that it does, it's going to do one action, right? It moves, and once it does the move, then the environment sees the action, it's going to change its state, right? So it's going to get from state ST into a state ST plus 1, right? Now, once it changes this state, it's going to give you one as well. So you're going to get this guy was at state st, it's going to change to st plus 1, st plus 1, and it's going to give you the reward rt plus 1, right? And now, this time you are going to see st plus 1. This is the observation that you are going to do, right? Everybody's cool? Questions? No question? Great. So, no question. Then let me just do one simple state representation of the system. That probably makes the story much clearer for you. Say the environment has the initial state S0, right? Board thing set for start, right? So you have S0, then you see an observation of that. Based on that, you're going to do action A0, right? Once you do action A0, you move your piece, right? And once you move your piece, the thing that is going to happen is that the state is going to change because the board is now changed, right? Now, as I change, you get it, right? Maybe your first move, you win. You are master, right? But you are going to get one reward. Maybe nothing happens, you get reward 0, right? That happened, now the environment is going to change, but the state that is going to change also, of course, depends on the move of the other side, right? The opponent is going to change, and now you have a new state. This whole new state is going to be S1. Now you look at this new state S1, you're going to do your next action, right? You look at the board, your move, the other side move, and then based on that, you're going to decide for your next move, right? So you see the new state of the board, and then you're going to decide for your move. Once you move, the state is going to change. You are going to get the reward, right? And you keep on going like this till time t, right? So you keep on going like this till time t. Now, at every single time when you look at this state, the only thing inside the environment which is going to impact the current environment is going to be the previous state, right? So if you want to know what is happening at time t plus 1, you look at the action at time t and the state at time t, right? And then the environment is going to just transit from state st into a state st plus 1. Everybody's clear? Questions? No question? Yes. It can impact the reward because you mean, yeah, you can think like that as well. You can think like that as well. It depends how you think about the state. But the key point, yeah, you can say that the impact of or the kind of R1 you get is directly coming only from the transit state. But if you want to be mathematically concrete, then that line could exist because your R could depend on S, I mean, like conditional distribution, S of the current time and the action. It could be. But yeah, I mean, if you want to think about like chess, it's quite fair to say that this is only, like this direct line is not necessary. Yeah. Yes? Yes, sure. But I didn't want to make it too much mess. I just wanted to show the evolution of the state. But you're right. That or, I mean, I'm not showing how this A is taken. Yeah. That is, of course, impacted by that. No. Questions? No question? Okay, great. So now, if all of these discussions make sense to you, now, based on this discussion, we can assume that this state is showing the property of Markovity. So what is Markov process? So what do I mean? I simply mean that the reward in the next time and the next state, which should be st plus 1. Sorry, here this guy is a typo. St plus 1. So the reward of the next at every single time, the reward of the next time and the state of the next time only depends on the last stage, right? So it depends which stage you are in, and then based on that, the next reward and the next state is somehow specified. Okay? So moral of the story, when you act with the environment is in some situation, you act, it's going to change situation. But this change, it does not depend on what was inside the environment many times ago, right? It only depends on the situation that the environment is on, right? Okay, cool. Now, one question that you might ask me is that can we guarantee that for any environment we're going to have such a state? Like, there is a simple answer, hard answer. Simple answer, yes, you can. Okay? So harder answer is that, well, under some very mild assumptions, any such sort of process can be eventually modeled as a Markov process. And it only depends how you define the state of that Markov process. And we don't care about that. Yeah? So any process that you see, like random process that you have, you can somehow collect it into a form that is actually order 1 Markov process, but the state of that process could be giant. And we don't care about this because at the end of the day, we want to get rid of this like completed state, and we want to work with the state that we can see. Okay? So theoretically, this is a kind of correct mathematical formulation, but if you don't see it immediately, that's totally fine. Just take it from my side, and trust me, I didn't make it by myself. I just took it from the literature. Okay? Okay, cool. So now I have the idea of Markov process. Markov process is a random process to see random things exactly like our environment, where the state at every single time is depending only on the state in the previous time. It means that if you want to know what is the chance of your next state being something specific, then given that you do know that your first state is S1, your second state is S2, till the last state was SD, you only need to know last state. You only need to take into account your last state. Anything before that is somehow encoded, captured inside the last state. Okay? Questions? Yes?
Is this explanation of state still valid when, or assuming if reinforcement learning gets into deep neural nets to represent the state?
Yes. Yes. Oh, neural network. Right. And then it's hard to say that you are getting the neural network to estimate the state, but you can say that the state goes as a kind of input to your neural network, right? That is correct, yes. It's still valid. This is still the thing that we do, yes. So I have a question. So this ST plus 1 told you, I just hope that it's not confusing. I told you that S state, this capital guy, which is this random variable, is something between from the set S1, S2, so on till Sn, right? Right? Now, these small guys, St plus 1, St, S1, all of them is one of these guys, right? Everybody's cool, right? So if your state is 1 and 2 only, right? So your first state could be either 1 or 2, right? Like a power key, right? And then your first state as 1 could be on, the second one could be on or off, the third one could be on or off or so, right? Everybody's cool. You get the notation, right? I do know it's one of the messiest topics to make slides on, but I do my best to just make a consistent notation. Okay, cool. So moral of the story here is whatever you want from the past is somehow encoded in your last state. And what you do always, you always think of your environment to be a kind of state-dependent entity, and then this entity is actually described by a kind of Markov process. Okay. Now, once again, you might have access to the state. You have the complete observation. And the other thing is that you are in one particular current state, you're going to do one action, and then the environment is going to look only on that state, and the action is going to give you the next reward, and it's going to change its state. Okay? Everybody's cool, right? Okay, cool. Now, yeah, this is just the indicator of what I said. So we could have the full observation. This is optimal case. We could have partial when they are not the same, the observation that you do in the true state. But to keep everything easy from now on, I'm going to consider full observation. That is going to make life much easier. And as you're going to see at the very end when we do deep RL, we actually do so much approximation that this one is actually nothing as compared to what happens there. Okay? Cool. Now, let me just quickly finish this modeling of the environment. So right now, what I have as the model for my environment is they're going to look at the actions that I do, and it's going to change the state and give me some reward. And if I want to write it down mathematically concrete, the way that I can do it by two functions. So one of them is rewarding function. This definition is a bit made up by me, but I just want to give it as a kind of concrete formulation. Then when we get into MDPs, then we're going to show that this reward function is eventually just a distribution. Okay? But right now, we have this reward function. What is the reward function? This is going to look at the current state as your current action is going to give you one reward from the reward set, right? Now, the key point about this function is that this function is not necessarily deterministic, right? It could be random. For example, it looks at this state and the action that you have done, and based on this action, it decides to give you either 1 or 2. 1 with chance half, 2 with chance half, right? This is one reward function, right? So the reward is a kind of random. In general, this is random function, which is looking at this state in action and is going to give you the next reward. You have a transition function as well. So the transition function is the function, again, random in general, which is looking at your current state and action, and it's going to decide what is going to be the next state, and it could be random again, right? So you can randomly choose between a couple of states, right? Everybody's cool? Okay, so now that I have the transition function, I have the reward function, everything is actually formulated. Now I can throw away all the story and I can just work with these components, right? Now, how you can specify the rewarding function and the transition function. They depend on the problem that you have. If, for example, you do have some sort of, say, for example, a chess game, right? It depends on the rules of the game, right? If you do some move, then there are some specific kind of states that the chessboard can get into, right? Not every state, right? And for some other case, there are sometimes a bit of randomness, obviously there, like when you're playing chess, this transition depends on the move of the opponent as well, right? So that opponent is the random component there as well. And also, in some other cases, it might depend on the physical dynamics of the system, right? In the robot arm example I told you, it depends on the physics, right? So you just do one action, and then you want to change the angle of this particular joint, right? That depends on the resistance of the air around it, the friction that you have, many other things, right? Physics are going to transition for us. And in most actually practical cases, we don't know that transition, and we typically do two approaches. One of the approaches is that we just simply do model that. This is what we have in the model-based approach. And one other thing is that we forget about the model as well. We just look at the data that we see from the environment, and we try to do some estimation. Okay? This is the model-free approach, which is the main thing we want to do, because modeling is going to be a nightmare in practical scenarios. Okay? Now,